Hello, my name is Paweł Sroka, I'm with Remedo Labs, and I'd like to present you ORAN Hierarchical Traffic Management applied in Advanced Vehicular Scenario. But before we go into the details, let me introduce the fundamental basis of the traffic management, which is the flexible UE to base station association that is used here. So when we consider a conventional radio access network setup, each UE performs the measurements of the received signal from each base station in form of RSRP measurements, and then is associated with simply the base station providing the strongest signal. Such an approach, although very simple, can lead to unequal load of all base stations in the network, which eventually in some critical cases might result in some base stations being overloaded, consequently with some UEs being in outage. This is of course undesirable situation in our network. So what we can do, we can apply load balancing, where we make use of this flexible UE to base station association by reallocating some of the UEs to other base stations in such a way that we try to equalize the load of all base stations. So such a situation should lead to the maximization of our network performance, because all the base stations will try to use as many resources as they can. And of course is the desirable situation in our network. However, this approach might not be always the best case, especially when we have a situation where we have some high priority services like some UEs, group of UEs, category of UEs, or maybe some category of services that require some special treatment. So we need to secure access and the continuity of the service. So in case of load balancing, it might turn out that some of those UEs might simply not get enough resources. So what we can apply then is to use the service-based traffic steering. So again, we use this flexible UE to base station association approach, where we move one category of UEs, probably those high priority UEs, to one or more base stations, and offloading all the other UEs to the other base stations. Of course, such approach results in unequal load balance between the base station, but we are able to secure enough resources to maintain the continuity of service for those high priority services, probably eventually at the cost of all the other UEs, which might experience some outage. So those two approaches create the foundation of the hierarchical traffic management we'll be discussing today. And to demonstrate the use of it, we'll use a mobility scenario where we have some vehicular and pedestrian traffic and different types of services such as mobile broadband, voice over IP calls, or some emergency connectivity. And we'll demonstrate the use of this hierarchical traffic management in a use case where we have some emergency situation happening at the Embassy Suites Hotel in Dallas City Center in Texas, US. So the main actors here will be some emergency special services, the pedestrian and vehicular UEs, which are the conventional UEs, then the first responders, which will be high priority UEs, which activate to handle the emergency situation, and a cyber attack perpetrator, which will try to disturb the normal operation of our network via the denial of service attack. And our main aim here will be to keep our network operational in any scenario. So we'll start in a normal mode where we have stable situation and we'll try to maximize the quality of service of all UEs. Then we'll move to the emergency mode where we have some high priority services like the public special service or the first responders. So we'll prioritize those services, whereas we'll also try to maintain the slice level agreements of all the other UEs. And finally, we'll move to the critical mode where we have this cyber attack. So we'll give very high priority to all the security services and also the emergency services, of course, at the cost of all the other UEs. When it comes to the detailed objectives, we'll try to minimize the outage, especially for those high priority services. We'll also try to guarantee the quality of service according to the slice level agreements. We'll try to maximize network performance. And finally, we'll try to minimize handovers for all those high priority services, if of course it is possible. To describe our use case in terms of time evolution, we can split it into 5 phases. We start in phase A, which resembles everyday traffic in an urban area of Dallas. So we have some pedestrians and vehicular users moving, connecting to the base stations with two types of traffic, so mobile broadband or voice services. But once we have this emergency situation happening at Embassy Suites Hotel, we move to phase B, where an emergency call is dispatched. And then in reaction to that emergency call, the first responders activate and the special service unit is dispatched from the emergency center and starts driving towards the Embassy Suites Hotel. Then we move to phase D as time goes by, where we have those special services finally arriving at the hotel and handling the situations. And also we have the first responders organizing the traffic, blocking the traffic in the surrounding area, so we'll have some traffic jams and crowd gatherings forming. And finally, we'll move to phase E, where we have this denial of service cyber attack in the central area, trying to disrupt our proper network operation. So we have represented our use case using the Sumo simulator, where we have some pedestrian and vehicular UEs moving on the streets, and we have 6 base stations, so violet macro base station and 5 green small base stations. We start in phase A, of course, of normal traffic, then we move to phase B once we have this emergency situation and emergency call dispatch at Embassy Suites Hotel. And in reaction to that, in phase C, we have the first responders activating and also the special service unit arriving in the area and driving towards Embassy Suites Hotel. So we see that we have this new high priority traffic, which actually puts some challenge to our network. And once this special service unit arrives at the hotel, we move to phase D, where we have this very challenging scenario of high priority services in the central area and also crowd gatherings and traffic jams forming because of the first responders blocking the traffic. And to add to that, to add more challenge to that, actually we'll move to phase E, where we have this denial of service cyber attack by one of the first responders, which turns out to be undercover villain and tries to disrupt our proper network operation. So to handle such a situation, we propose to use the hierarchical traffic management approach using the rMedo solutions. So we propose here to use 2 of our applications, which are the traffic management rApp and traffic steering xApp, which are deployed using the VMware Run Intelligent Controller, and they react to the network state and try to impact the operation of the network, which is represented by the run simulator provided by rMedo Labs. So when it comes to the functionality of the 2 applications, the traffic management rApp, it is responsible for observing the network status, the network performance via O1 interface, also receiving some additional enrichment information from external sources like the external databases, and based on that, it generates a set of policies which are sent over A1 interface to traffic steering xApp. The traffic steering xApp is responsible for issuing some instructions to the E2 nodes, so our base stations mainly, in the radio access network, which actually are in the form of handover control messages, and according to the specified policies provided from the traffic management rApp, it tries to enforce either service-based traffic steering or load balancing. So simply the traffic steering xApp via the handover control messages enforces the policies specified by the traffic management rApp. So we can say that this hierarchical traffic management system makes use of the following key features, right? So we have some automated policy selection, which are performed by the traffic management rApp, and these are very suitable for this heterogeneous network scenarios. Then we can make some decisions on a per user per slice basis, so mostly concerning the UE association. And we can also try to minimize the number of handovers by performing service-based traffic steering and also minimize the outage. And finally, we can also employ load balancing in forms of specific policies to maximize the network performance. So overall, we have very, very flexible approach to the management of our network performance. So to demonstrate the capabilities and performance of such hierarchical traffic management, we present the simulation results where we compare the performance of 2 setups. So we have a reference system where we use the conventional association, which is RSRP based. So the UEs are associated with the base station based only on RSRP. And we have this rMedo setup, which makes use of this hierarchical traffic management approach, where we have this traffic management, traffic steering applications enforcing either load balancing or service-based traffic steering. And we compare the performance in form of three measures here. So we have this cell load representing the amount of used resources in the cell. Then we have the number of connected UEs, average number of connected UEs, and the outage rate of UEs. And we start in phase A, where we have quite stable situation. So the network is moderately loaded. We have only around 40 to 50% of network load, that's the cell capacity used. We have no outage, so situation is very, very comfortable for us. We can apply a normal mode policies here with the remedial solution, where we mostly perform load balancing. When we move to phase B, there is not so much change in the performance of the network and behavior of the network, although we have this emergency situation, emergency call is dispatched, but still the environment is unaware of what's happening around. So still the performance of the reference approach and the remedial solution are very, very similar. But situation starts becoming interesting when we move to phase C. So this is the phase where we have this high priority first responders and special service unit arriving in the area. So these are the high priority services, very, very demanding in terms of resources, especially the special service unit. So we see that we have already some increase in network load, and that increase for base station number 4 and 5 is more significant in case of reference solution than a remedial solution, which is the result, of course, of those high priority services being UEs being associated with either small base station number 4 or 5. Situation is different with the remedial solution because those high priority services are associated with macro base station. So this is the result of applying the set of emergency mode policies, which are applied in a proactive way here, which simply state that we should associate all the high priority UEs, so the special service and first responders, with the macro base station and offload all the other UEs to the small base stations. So this results actually and these differences of in network load and base station load already appearing. So we have network load increasing, but still node outage here. And the changes here in the performance of the network become visible when we move to phase D. So the phase where we have already this quite challenging situation, the central area. So we have the special service unit here near Embassy Suites Hotel. We have also the first responders blocking the traffic, so we have traffic jams forming and crowd gatherings. And we can see that for the reference scenario, we have particularly heavy load in small base station number 4, which becomes overloaded, right? And we already have some outage appearing, so we have over 80% of outage here for the UEs. This is the result of the high priority special service unit being associated with the small base station number 4, which consumes most of its resources, so there is no room for all the other UEs. Situation is still manageable with the all other base station, but already still becomes challenging. It is different when we consider the remedial solution, when the traffic steering and traffic management is applied. So according to the traffic steering and traffic management policies, we move this high priority traffic to macro base stations. So we can see that the load of macro base station in case of remedial solution is much higher than in the reference case, although the number of UEs we have in here is much lower than in reference case. This is because we have all those high priority and very demanding UEs associated with macro base station, whereas all the other conventional UEs are moved to the small base station. So application of such policies actually allows us to, of course, first of all, secure the resources for this high priority traffic in macro base station, minimize the number of handovers, but also it relieves the resources in the small base stations to all the other UEs. So in such a case, we see that we have reduced load of this base station number 4, and we have no outage, which is very beneficial for us. And the difference in performance becomes even more visible when we move to phase E, so the phase of the cyber attack launched here by one of the first responders. So in such a case, we see that for the reference network, actually situation becomes unacceptable. Actually, the network is, we can say, is no longer operational, because for the 3 central base stations, so base station, macro base station number 0 and base station number 4 and 5, situation becomes critical. So we have over 90% of load, even 99, over 99. And we have very, very severe outage, right? So we have over 50% or even over 70% outage for the base station number 5 and 4 respectively. The situation is very difficult also with the macro base station. So basically we can say we have no connectivity here in the central area. It is different when we consider the remedo solution. Because of the traffic steering and traffic management applied, we can apply some critical mode policies which allow us to deny service to the denial of service a cyber attack perpetrator once it's detected. So we can simply specify that particular UE might be denied access to our network, which results only in some minimal outage, which is mostly to the detection delay of this denial of service perpetrator. So we are able to maintain the network operational and to provide those critical the resources for the critical services by issuing this critical mode policy, which actually allows us to exclude that malicious user from the network. So in general, we can state that during the whole simulation, we observe quite significant changes in traffic and also in network performance. We have some high priority UEs appearing and consuming most of the resources, which is quite challenging situations for the reference system because it struggles to provide the necessary services, and we see already some significant outage, especially in the case of the cyber attack. Whereas the use of remedo traffic steering and traffic management give us the adaptivity and flexibility in allocation of resources, so we can serve the high priority UEs by the macro base station, whereas we are offloading all the other lower priority UEs to small base station. And we have also the possibility to exclude the malicious user from accessing the network, which allows us to maintain the network operational in all situations. So we can say that we have network operative in all conditions, and we experience only some minimal outage, mostly due to the detection delay of the cyber attack. To provide more in-depth overview of what happens in a system, we can take a look at some time series. Here we represent the macro cell load, so the load of base station 0, and the total system outage. So of course, once we start with phase A and then move to phase B, situation is quite stable. We have around 50% of the macro cell load. We have no outage in the system. But the interesting thing starts to happen when we move to phase C. So we have the special service unit and first responders activating. And we see that the macro cell load starts increasing. The increase is moderate in case of reference system, but quite significant in case of remedo solution. The reason for that is that actually, according to the applied policies, we serve all the high priority traffic with the macro base station, so we consume almost all of its resources. It might seem not so beneficial, but it pays off when we move to phase D, where we have the special service unit arriving at the hotel, and we have already some crowd gatherings and traffic jams forming. Because we see that in phase D, we already can observe some outage in the reference system. This outage is mostly related to this base station number 4. Whereas with the remedo solution, because the high priority and demanding traffic was offloaded to macro cell, we still have 0 outage. And as we move to this challenging phase E, where we have the cyber attack, we see that situation becomes unacceptable for the reference system, as we have quite severe system outage. It's around 30, almost 30%. So basically we can say the network is no longer fully operational. Whereas for the remedo solution, we see that we have only some temporary increase in the outage, which is due to the detection delay of the cyber attack. So once the cyber attack is detected, we can simply exclude that malicious user from the network, and network returns to its normal mode of operation, the proper mode of operation. So to summarize, we propose here a hierarchical traffic management approach, which is comprising the traffic management rApp, which is responsible for issuing the traffic steering policies, and the traffic steering xApp, which actually is responsible for applicating those policies by proper association of UEs with the base stations according to the rules specified in those policies. So the aim here is to optimize the utilization of available resources. So the application of such hierarchical traffic management allows us to keep the network operational in all the considered operation modes. So we have both the normal mode where we perform the load balancing, but we have also those challenging emergency mode and extremely challenging critical case where we have this denial of service cyber attack. With this hierarchical traffic management, we have also the ability to give priority to some particular services like the emergency services, the first responders, and we can also try to maintain the slice level agreements of all other UEs by proper traffic steering. We have also an option to deny a service to a particular UE, like the denial of service perpetrator, once it's detected. So all in all, we can say that we have a very, very flexible and adaptive way of changing strategies of resource allocation, which of course is based on the observations of our radio access network and can be also supported with some enrichment information which is provided from some external sources like the external databases. So thank you for your attention. If you have any questions, of course, don't hesitate to contact us. And obviously, the best regards from the whole Remedial Labs team. Thank you.